Now, if you take the pressure to be the atmospheric pressure, which is 1 atm, and the T is 0 degree of Celsius, which is 273 Kelvin, and if we have 1 mole of gas, we will have the volume of 22.4 liter. And this is what we call the standard temperature and pressure, or the STP. A different law that we will also discuss is the Daltons law of partial pressure. In the case where we have a container and then we have two different gases, say gas A and gas B, and in the condition where the gases do not react with each other, we can calculate the mole of A and also the mole of B. We can calculate another parameter that is called the mole fraction, symbolized as an X. So X is equal to, for instance, in the case of A, it is equal to the mole of A divided by the total mole of gases. In this case, it's going to be Na plus Nb. Similarly, Xb is going to be Nb divided by Nt by the total of Na plus Nb. The Daltons law ruled that the pressure of A is equal to the mole fraction of A multiplied by the total pressure, while the pressure of B is the mole fraction of B multiplied by the total pressure. The total pressure itself is, of course, the sum of the partial pressure of all the gases. So the PA is partial pressure of A, PB is the partial pressure of B, and the PD is the total pressure of the system. Now, for the mole fraction, the sum of all mole fraction will always make up to 1. Now we will discuss the kinetic molecular theory of gases. Now, the ideal gas that correlates with the ideal gas equations actually was derived based on several assumptions. First, a gas is made up of a vast number of particles, and these particles are in constant random motion. And the speed of the moving gas particles is equivalent to the square of 2RT divided by the m, which is the mass of the gas, that is AR, or the MR of the gas. The second assumption is that the particles in a gas are infinitely small, that they occupy no volume, or the volume of the gas itself is considered to be 0. The third assumption is that the particles in a gas move in straight lines except when they collide with other molecules or with the walls of the container. And the collisions with each other and also with the walls of the container are presumably elastic, so the total kinetic energy of the particles is conserved. The average kinetic energy of the particles in a gas is proportional to the temperature and does not depend on the identity of the gas. The higher the temperature is, the faster the speed of the gas, and also the lighter the mass of the gas is, also the faster the speed is. It is important to realize that all of the molecules of the gas do not move in the same speed, and they actually move in different speeds, that if we plot the number of the particles or the fractions of gases that move in a certain speed, we will get this distribution that we call the Maxwell-Boltzmann distribution. And the V that we discussed about before is the most probable speed with the highest amount of particles moving at that particular speed.